Okay, thank you. All right, so the first thing I want to talk about today is just one interesting and often useful feature of the Hamiltonian, and then we'll do an example picking up from last time where I was talking about the minimum principle, which is that we know that the Hamiltonian is equal to the Lagrangian plus the inner product of the costate with the right-hand side of the dynamics. Now, you'll recall that the equations that come out of the optimality conditions, and I've written these down many times at this point, look like that. These are the Hamiltonian equations. So from this, you can actually see something kind of interesting, which is, let's suppose I write these in scalar form. So in scalar form, the way they look is xi dot is equal to minus h lambda I, sorry, plus h lambda I, and lambda I dot is equal to minus h xi. And these run I going from 1 up to n. So what you'll see from this is that, let's suppose we look at this as in terms of a product, a summation and a product as follows, which is that, let's suppose I take dh dt. What do I get? Well, we know that the Hamiltonian in general is going to be a function of the state, the costate, the control, and time, right? But assume now that I've solved for the optimal control. So the way to, well, so maybe I'll put one step in here before that. So assume that we have found an expression for u star in terms of x star, lambda star, and t. So that would say u star is equal to u star of x star, lambda star, and t. Then the Hamiltonian is going to be a function of the optimal state, the optimal costate, and time, because I've taken the control out, because it would also be a function of the control, but it's been explicitly solved for in terms of the others. So now let's suppose I take dh dt. So dh dt is going to equal what? Well, it's going to equal the sum from I equals 1 to n of the partial of h with respect to xi times dxi dt plus the partial of h with respect to lambda I times d lambda I dt. This whole thing is in the summation. Plus the partial of h with respect to t. So the dependence on time occurs in all of these, right? X is a function of time, lambda is a function of time, and then there's t explicitly. But we know from the previous equation that dh dt, I mean dh dx and dh d lambda are related as follows. So what do we get here? We get the sum from I equals 1 to n. So I know that dxi dt is x dot, but x dot is equal to h lambda. So what I get is I get the partial of h with respect to xi times the partial of h with respect to lambda I. And then I get the partial of h with respect to lambda I, but you'll see that d lambda I dt is minus dh dxi, so I get minus, and then I get the partial of h with respect to xi, and then I've got this other term over here, plus the partial of h with respect to t. So you can see that the first two terms, the whole summation cancels out, right? Because this is the same as this quantity over here. So this is just equal to the partial of h with respect to t. So it says that the rate of change, or the total derivative with respect to time of the Hamiltonian, is only the partial with respect to time of the Hamiltonian, which means if the Hamiltonian's not an explicit function of time, so suppose that h is not an explicit function of time. When I say explicit function of time, I mean that time does not appear as an argument in one of the dependencies here, right? It's implicit. It's always implicit through x and lambda, but it doesn't explicitly appear. So it's not an explicit function of time. Then what that says is it says that the partial of h with respect to t is going to equal 0, which means that dh dt is going to equal 0, which implies that the Hamiltonian along an optimal solution is going to be a constant, right? So the Hamiltonian's constant in the case where it's not an explicit function of time. Now, if you remember, if I go back through, I always have to pull these things out because I never get my signs straight on these things. But if you remember the transversality conditions, you have the following. So let me just pull these transversality conditions out so we can get the signs right. And the only one that matters here is the one on the final at the final time. But we remember that lambda of t0 is equal to minus d phi dx at t0, and then plus, well, lambda t0 transpose is equal to this. And then I've got plus nu transpose times the partial of phi with respect to x at t0. And I've got lambda transpose at tf is equal to the partial of phi with respect to x at tf. And then I've got minus nu transpose times the partial of phi with respect to x at tf. So now let's take another step here, which is that if you look at this, you'll see that and we've got h at t0 is equal to partial of phi with respect to t0 minus nu transpose the partial of little phi with respect to t0. And then you've got h at tf is equal to minus the partial of phi with respect to tf, and then plus nu transpose times the partial of phi with respect to tf. So let's look at this condition right here for just a second. So suppose, again, that h is not an explicit function of time. So we know that h star is going to equal a constant. Now, let's look at another condition here, which is that also now, suppose that tf is free. Because if tf isn't free, we can't add this other condition. If tf is free, we can see that in this condition right here, if these conditions here, if neither phi nor little phi depend explicitly on tf, then what's true? If neither of them depend explicitly on tf, then the partial of phi with respect to tf is going to equal 0, and the partial of little phi with respect to tf is also going to equal 0, right? If that's the case, then that says that h at tf is going to equal 0. But we already know that h star is a constant, right? Because it's not an explicit function of time, which implies that the optimal Hamiltonian is going to equal 0. It's really important to know, this is something that you won't find in a textbook. Most textbooks will tell you that if the Hamiltonian is not an explicit function of time and the final time is free, then the optimal Hamiltonian is 0. But that's not correct. It's if the Hamiltonian is not an explicit function of time, the final time is free, and these two functions don't depend on tf explicitly, then the optimal Hamiltonian is 0. And I'm going to give you an example of where this comes up. We're going to do an example in just a few minutes, which is going to do a lot of different stuff, but this is going to be one of the things that's going to happen. So I'll show you exactly what I'm talking about. Let's look at this example now, because this example does a bunch of different things, and I love this problem, by the way. like when people study different problems in optimal control, this is true in any subject, but one of the great things about optimal control is you do not have to make a problem mathematically complicated in order for it to be a difficult problem. And a great example of this, are you in chemical engineering? You are in chemical engineering, so this applies to you. Okay? This is actually very important. In many applications, in particular when we deal with like mechanical systems, like if you're dealing with robotics or if you're dealing with vehicles, vehicles generally have what are called two-sided control. Two-sided control means that if you can do something in the positive direction, you can also do that same thing in the negative direction. Think of like a car, right? Now, in reality, you can't do the same thing in the negative direction, but you can go in forward and you can go in reverse, right? And like in many systems, you can reverse the direction of an effect of a process. If you have an arm rotating, you can apply a torque this way to rotate it that way. You can apply a torque the other way to rotate it the other way, right? So your control action can be in either direction. In chemical engineering, a lot of processes don't have that. A lot of processes have what's called one-sided control. One-sided control is a nuisance. Think of a chemical process, for example, where you've got chemicals being put into a system. Once you put chemicals in, you can't take chemicals out. That's it. If the process is to mix, to do some sort of mixing where you're mixing different liquids together to come up with a new liquid, once the stuff goes in, it's not coming back out. So that's it. It's one-sided control, which means that your control is bounded by zero. In fact, it turns out that chemical engineering problems, some of them are so difficult to solve. And you will look at them and you will say, that can't be a difficult problem. It looks so simple. And you say, yeah, it looks really simple until you actually try to solve it. And then you realize that what's making it difficult to solve is the fact that the physics don't allow you to do things that you otherwise would normally want to do. You would want to reverse something that if you could do something in a positive direction at some point along the process, you may want to do it in a negative direction in another part of the process. In a lot of chemical problems, you can't do that. You can't reverse the direction of the input to the process. It can only go one way. The least it can be is zero, which means you do nothing. So don't ever let like the complexity of an optimal control problem fool you, because many problems look simple, but they're actually really complicated. Here's a problem that on paper looks really simple, okay? This is what's called the minimum time double integrator plant. It's a classic problem in optimal control. And it's the minimum time double integrator. The problem statement is as follows, is that I'll draw it for you in a sort of sense of a mechanical system first. You have a mass on a spring, and you can apply a force to it. Okay? The goal is starting at some initial displacement and initial velocity, drive the mass to zero displacement and zero velocity in minimum time. Now, clearly when you're dealing with a system of this nature, what would be the optimal solution? Let's just think. Suppose F, which is my input, F is unconstrained. I can make F anything I want to make it. The optimal solution would be to apply an infinite force to be able to get it there in zero time. Because if I can apply an infinite force, I can change the velocity instantaneously to drive it to whatever point I want, right? I can literally apply an infinite force that will go and put this thing right at the origin, right? That's physically not a realizable problem, right? You can't apply infinite force, right? You can only apply finite force. So infinite force is not reality. So generally speaking, so in reality, f of t is bounded, right? There's going to be some maximum amount of force we can apply. There's going to be some minimum amount of force we can apply. And it's going to be a finite value, right? So f of t is going to be bounded by some maximum amount, right? Because otherwise this problem doesn't make any sense, right? Now, let's look at this problem in that particular case. So the dynamics of the system, if you write them in second order form, I won't go through any derivation. This is not a dynamics class. It's mx double dot plus kx equals f of t. It's a simple system. It's just it's an oscillator, right? It's not really that big a deal. So we can rewrite this as x double dot is plus k over m x is equal to f of t over m, which we'll just define as u of t. And now what we can do is, just for simplicity, because it doesn't change the solution at all if we change these numbers, let m equal k equal 1. So then what we get is we get x double dot plus x is equal to u of t. So that's the system. So the problem is we're given x at 0 equals x0 and x dot at 0 equals x0 dot, because clearly those are the initial conditions, and we want x at tf to equal 0 and x dot at tf to equal 0, and we want to minimize time. So if we do this with the state space model, which is normally what we do, is we say let x1 equal x and x2 equal x dot. So then what that gives us is it gives us the following first order system. x1 dot is equal to x2, x2 dot is equal to u, and I've got the boundary conditions that x1 at 0 is equal to x1 0, and x2 at 0 is equal to x2 0, x1 at tf is equal to 0, and x2 at tf is also equal to 0, and the cost function is tf. I want to make that as small as possible. So that's the optimal control problem. But I told you that f of t was bounded by f max. So there's another thing in here, which is u is bounded to lie between minus u max and plus u max. And again, for simplicity, but it doesn't lose any generality, let u max equal 1. You can make these numbers anything you want, but for the purposes of instruction, it's just easier to normalize everything so that everything's at 1. Okay? So we know the system is controllable. That system is controllable. You can drive something to the origin in finite time with this system, and you can just check the controllability condition, and you can see that. So so this is the problem. Now, let's look at this. So we want to determine the optimality conditions for this problem, okay? And we want to determine the optimal solution. So how are we going to go about doing this? Well, we do this the way we start any optimal control problem. Is the first thing we have to do is we have to determine the Hamiltonian. So we know that the Hamiltonian is equal to L plus lambda transpose F. But L is 0 because I have a Mayer cost. That's all I've got there is a Mayer cost, right? So this is equal to lambda 1 x2 plus lambda 2 times u, right? Lambda 1 times x2 plus lambda 2 times u. Now, look what happens. So if you're going about, this is the sort of starting point of optimal control, right? So if you're going about this naively, let's suppose we know one of the optimality conditions in the case where the optimal control lies on the interior of the allowable control set. The allowable control set is between -1 and 1 in this case, right? So if I take the partial of h with respect to u, what do I get? I get lambda 2. Can I solve for the optimal control using this? No, this is not a function of control, right? This is not a function of control. So this does not give me any information on the optimal control. And it shouldn't, because if it did, it would say that the optimal control lies on the interior of the control set. But if the optimal control lay on the interior of the control set, it would say that it would be better to do less to get you there in a shorter time
than it would be to possibly do more, meaning either at the upper extreme or the lower extreme, right? But that wouldn't make the costs as small as possible. That would increase the amount of time it took to actually do this, right? Think about it. Let's suppose that if I was plotting control here, right? This is just a qualitative plot. And here's 0. And I just do just a little bit more than 0, just barely more than 0. Clearly, it's going to take me a long time for that control to have any effect on the motion of the system, right? Because it's a very, very small magnitude control. So if I'm going to do that, I might as well do just a little bit more. If I'm going to do that, I might as well do just a little bit more. Well, I might as well just do the maximum, right? Similarly, if I'm doing just something just slightly negative, right? Well, it's probably better off that I do something a little bit more negative. And this is a very qualitative assessment, by the way. I'll go through it rigorously in a minute. And even more negative until finally I'm just doing the absolute minimum amount of the lowest amount of control effort in sine, lowest amount of control effort. But this is +1, and that's -1. So intuitively, it would seem like the better thing to do would be to operate at one of the boundaries. All right. So let's see how we actually do this. So this is a useless condition for this problem. So what we have to do, because this condition doesn't get us anywhere, is we need to actually apply Pontryagin's minimum principle. So Pontryagin's minimum principle for this problem will look like this. So here we go. We know that the optimal control is the argument of the minimum of u, which in this case is on the interval -1 to +1, of h, which is equal to the argument of the minimum of u in -1 to +1 of what? Well, the Hamiltonian is λ1 x2 plus λ2 times u. So what this says is, find me the value of the control that at every point in time minimizes the Hamiltonian. Well, let's look at this again. Let's look at this now. Let's suppose the control were positive. Well, let's look at the other way. Let's suppose the costate, λ2, were positive. If λ2 were positive, what would make, because this doesn't have anything to do with the control. I can take it out, right? This really amounts to argument of the minimum u in -1 to 1 of λ2 times u, because this is not a function of the control here, right? So this is not going to affect, and I can make this anything I want. It's not changed by the control, right? It doesn't have any, the control has no effect on this term whatsoever. So the only thing I'm doing is I'm dealing with this term over here. Let's suppose λ2 were positive. If λ2 were positive, what would I want the control to be to make this as small as possible? Suppose λ2 were 5. Well, -1, right? What if λ2 were +5? Then, -5. λ2 is -5. Then I'd want the control to be +1, right? So the optimal control is going to be minus the sine of λ2. It says that it's equal to +1 if λ2 is less than 0, and it's -1 if lambda2 is greater than 0. Now, the only problem with this is what happens if lambda2 is equal to 0 on a segment, right? So if there's a segment along the trajectory where lambda2 is equal to 0, neither one of these conditions is going to apply, right? So we have to rule out the possibility that lambda2 can actually equal 0 on a segment for this particular problem. So let's go through the optimality conditions, the rest of the optimality conditions first, before we come back to this. We know that lambda1 dot is minus hx1, and lambda2 dot is minus hx2, because those are the costate equations. What is negative hx1? Well, what's hx1? Just look at it. What is it? 0, right? So this is 0. What is hx2? It's lambda1. So this is minus lambda1. So what this says is it says that lambda1 is equal to a constant, right? Well, if lambda1 is equal to a constant, so let's call this constant lambda1 bar. So what's lambda2 of lambda2 equal? Lambda2 is equal to minus lambda1 bar. So, sorry, lambda2 dot. So what's lambda2 equal to? Well, it's equal to minus lambda1 bar times t plus lambda2 bar, right? It's equal to that plus another constant, right? Yes? So what it says is, it says that the first costate, the first component of the costate, is a constant. The second component of the costate is a straight line, right? This is the equation for a straight line. So now we know that the optimal costate is a straight line. What are the possibilities for a straight line? What can a straight line have? It can have a positive slope and a positive intercept. It can have a negative slope and a negative intercept. It can have a positive slope and a negative intercept, or a negative slope and a positive intercept, right? So what the costate can look like is this. There are only 4 possibilities. There's nothing else, which is that if I'm going from 0 to TF, the possibilities for that lambda 2 are as follows, is that lambda 2 can look like this, if this is 0. Lambda 2 can start off positive, and it can stay positive the entire time. Let's make this a little smaller. This is TF. Right? That's possibility 1. What's possibility 2? Is that lambda 2 can start off negative, and it can stay negative the entire time. Right? The third possibility is that lambda 2 can start off positive, and it can go negative at some point during the interval. Or lambda 2 can start off negative and go positive at some point during the interval. Right? Those are the only 4 possibilities. This is lambda 2. Okay. Let's take possibility 1. If lambda 2 is always positive, what's the optimal control? Negative 1, right? So the optimal control is going to be negative 1. This is going to be u star. If lambda 2 is negative, what's the optimal control? It's positive 1, right? What if lambda 2 switches from positive to negative? Then the optimal control switches from negative 1 to plus 1, right? If the opposite is true, lambda 2 starts off negative and goes positive, then the optimal control switches from plus 1 to negative 1. Those are the only 4 possibilities, right? Because if lambda 2 were identically 0, let's take the case where lambda 2 were identically 0. If this were identically 0, then this problem has no meaning. This problem has no solution whatsoever. It says that it's a condition that cannot exist. If lambda 2 were 0, that would mean that this thing would remain 0 the entire time, and the control would never take any effect on this problem whatsoever. So lambda 2 cannot be 0. It has to switch from positive to negative, or it has to be one sign or the other. So let's look at now. Let's look at the. Go over here. Let's look at how we're going to actually figure this out now. So what we know is that the optimal control. So possibilities for optimal control. These are the only possibilities. You can either be always plus 1. You can go from plus 1 to negative 1. Sorry, always be negative 1. You can be plus 1 and switch to negative 1. Or you can be negative 1 and switch to plus 1. Those are the only possibilities, right? So now let's look at, let's suppose that, just for simplicity, let's say let S equal plus or minus 1. It'll make the rest of this analysis a little easier if we do this. We know that x1 dot equals x2 and x2 dot equals u, but that's equal to S because I just set it equal to that, right? So we know that what happens here is when we integrate this along an arc where, let's just take the first case. Let's take the case where S is always plus 1. So if S is plus 1, then what do we get? We've got x2 of t is going to equal t plus x2 at 0, right? Because S here is plus 1. So if I integrate it once, I just get t plus x2 at 0, right? So if I integrate that again, what do I get? I get x1 of t is going to equal 1/2 t squared
plus x2, well, let's write this like this, x20, plus x20 times t plus x10. Okay? So that's the solution you get. If s is equal to -1, then we get x2 of t is equal to minus t plus x20, and x1 of t is going to equal minus 1/2 t squared plus x20 times t plus x10. In either case, we get a quadratic as a function of time, right? Now, there's a point in there. That takes care of this case, and it takes care of this case. Now, in the other two cases, where we go from -1 to +1, or vice versa, let's suppose we switch from -1 to +1. So there's going to be a point. So let t sub s be the point, or the value of t at which u switches from -1 to +1, or from +1 to -1. So in the case, let's take the first case where s goes from -1 to +1. So in that case, what you'd get is you get x2 of t is going to equal minus t plus x20, and that's going to be for t less than or equal to ts. And then what you're going to get is now at the switch point, when you switch to +1, now what you're going to have to do is you're going to have to say x2 of t is going to equal, it's going to be plus t minus ts, and then plus x2s for t greater than or equal to ts. So if I plug in t equals ts into this equation, I get x2s, where x2s is equal to x2 at ts, which is the value I get when I plug this in up here, right? So if I go the other way, if I say, and now of course you integrate one more time to get x1 of t. So x1 of t is going to equal minus 1/2 t squared plus x20 times t plus x10, and that's going to be for t less than or equal to ts. And then x1 of t is going to equal, now you're going to have what? You're going to be integrating this across to the next, so you're going to get 1/2 t minus ts squared, and then you're going to get plus x2s t minus ts, and then you're going to get plus x1s, where x1s is equal to x1 at the switch point. All right? So you're going to get the same thing if you take the second case where you do this for s going from +1 to -1. So all this stuff is just going to reverse. You're going to get x2 of t is going to equal t plus x20 for t less than or equal to ts, and x2 of t is going to equal t minus ts t minus ts minus t minus ts plus x2s for t greater than or equal to ts. And then x1 of t is going to equal 1/2 t squared plus x10t, plus x20t plus x10 for t less than or equal to ts, and it's going to equal minus 1/2 t minus ts squared plus x2s times t minus ts plus x1s for t greater than or equal to ts. So basically, you get these curves as a function of time
where you can see that x1 of t is always a quadratic as a function of time, and x1 of t is, x2 of t is linear as a function of time. So you either get something that's linear or you get something that's piecewise linear, right? In either case, what you get really, you get these curves that look like this. You get these curves that, I don't want to draw this in color. I have colored chalk here, but I don't want to draw this in color. If you were to plot x1 and x2 is like a phase portrait, what you get is you get these two curves that are parabolas that open up like this. And one of these parabolas, of course, I never know which one's which, so I've got to go look at my picture. Hang on a minute. So I drew this a long time ago. So this curve here is s equals plus 1. This curve here is s equals minus 1. And what you get is you get a whole family of parabolas that a bunch of them open up to the right and a bunch of them open up to the left. And the optimal solution is if you pick a value, an initial, because remember, we're trying to drive everything to the origin, right? So what happens is if I extend this out so that these curves go into the other half here. I don't want to draw too many curves. It gets really confusing. Is that you will either already be on this curve. So this curve here, s equals plus 1, is the curve that you're on if you're starting and you never switch from one control to the other. What it says is if you start on this curve where s is equal to plus 1, from that point, you will just go straight in to the origin, applying plus 1 the whole time. If you start on the curve negative 1, it says that you will go in to the origin on that curve, and it doesn't make a difference. But if you start off one of these, then what it says is that in order for you to get to the origin, you first need to apply control to get yourself onto this curve, and then you drive yourself into the origin. And so there's the switch right there. You get a switch where you start on one of these curves, and then you wind up driving yourself into the origin on the other curve. So you get it. So there's a switch point, and that happens with all the other curves except for the ones that already naturally pass through the origin. The two parabolas that naturally pass through the origin, you never switch. You always stay on that curve the entire time. But if you're not on one of these parabolas that passes through the origin, then you're either going to go from negative 1 and then switch to plus 1 to go in, or you're going to go from plus 1 and switch to negative 1 to go in. And in order to solve for these curves, it's just a bunch of like tedious algebra to solve for all this stuff. But what the curves look like is they look like this. I'll see if here. This is what they look like, which is that you get the equation for these curves is this. Is that x1 is equal to x10 plus 1/2 s times x2 squared minus 1/2 s times x20 squared. And you get t, which is the optimal time, is equal to s times x2 minus x20. So that gives you the value of time. So that gives you the solution. So you can see the parabolas here. This is x1 as a function of x2, which is why these parabolas open to the right and left. They don't open up and down, because I'm writing x1 as a function of x2. So x1 is quadratic in x2. And so this gives you the way to parameterize where you are. So if you start with an initial condition x10, x20, this will tell you whether or not you have to switch or whether or not you don't have to switch. You'll know whether you're already on a curve that goes to the origin, because this curve itself will either pass through the origin or it won't pass through the origin. If it doesn't pass through the origin, then you're going to have to switch to go from one to the other. So you can see that this problem is really interesting because it doesn't have, it's a really simple problem from a mathematical perspective, right? There's not much going on mathematically. It's a simple mass on a spring with a force, right? That's all it is. It's a very, very simple problem. You guys could have derived the differential equation for this back when you were like, freshmen in college, right? Because, there's nothing going on here, right? It's just mx double dot plus kx equals f of t. There's nothing going on here. The only thing that's happening is I'm imposing this cost function that says that the optimal control is the one that has to minimize the time, and I have a bounded control effort. I cannot have an infinite amount of control. I have a finite amount of control effort. That's the key. And the fact that you have a finite amount of control effort and you're trying to minimize time, because you get this problem where the Hamiltonian is linear in the control, dh du, which is the condition you would apply if you were solving for a control that appears on the interior of the allowable control set, isn't a valid condition to be able to get you the optimal control. You have to apply Pontryagin's minimum principle. Now you can imagine that this is a double integrator plant. If you have like a triple integrator plant, then you're going to wind up getting potentially more than one switch, right? Because for every integrator that you add into the system, you wind up adding one more polynomial degree to your solution. Here we've got a quadratic, right? If I had a triple integrator, I'm going to have a cubic. So I could potentially have more than one switch, right? Because my costate's going to get more complicated. It's not necessarily going to be a straight line anymore. These were straight lines, right? But that's not necessarily going to give you a nice straight line solution. And if it does, it may be piecewise linear, and it may switch more than once, right? So you may actually cross the origin more than once. So these problems get very complicated, and you can do this actually. If you're doing controller design, you often want to add integrators into a loop to be able to get rid of steady state error. So you could actually wind up in a situation where you want to add an extra integrator in the loop in order to smooth out a process. If you do that and you're trying to minimize time and you've got some mechanical system of this kind, this can get to be a very, very difficult problem. So even though these problems look really easy, they actually admit these very exotic kind of solutions. And this is just for a double integrator that you get this. For other kinds of problems, I'm going to talk about in a few weeks. I'm going to talk about problems for which, remember I mentioned to you that the conditions for the costate and the optimal control were that the optimal control was +1 if the costate's negative and vice versa. And I said that we had to rule out the possibility that you could have an arc where the costate was 0. Well, there are some problems for which that does actually appear, where you get an arc where the costate's actually 0, and you cannot determine the control. Those problems are what are called singular arc problems, and I'm going to talk about singular arc problems later on in optimal control too. And if you're doing optimal control in chemical engineering, you have problems that have major numbers of singular arcs. Singular arcs are all over chemical engineering problems. And so it's largely because of the bounded control, the one-sided control. You get like these bioreactor problems. A lot of them just go from one singular arc to another. They're always on a singular arc. They're just on different singular arcs. They're really painful problems to solve. So it's like, I don't solve chemical engineering problems. I just look at them and just stay away from them because I know they're going to be really, really difficult. So, but actually, to be honest, most of my research is in computational optimal control, and the singular arc problem is one that has still never really been dealt with computationally very, very well. There are special cases where you can do certain things, but computationally, no one has ever really come up with that really slick method that can actually identify singular arcs numerically. It's really hard to identify singular arcs numerically. One of the famous problems like this, where you would think that you would actually go through this kind of an analysis, is what's called the Goddard rocket problem. The Goddard rocket problem is it's a maximum ascent of a sounding rocket. So it's just a one-dimensional rocket. You're literally firing it vertically, and you want to maximize the final altitude. That's the goal. Free time, you want to maximize the final altitude, right? That problem, the solution actually lies on a singular arc. There's an arc on the trajectory where the control is max, and then it goes along the singular arc, and then it's min. Most people, when they did that problem originally, thought it was a bang-bang control that went from max to min because you would fire the thruster and then turn it off. Turns out you don't fire the thruster and turn it off. You fire the thruster, then you fire the thruster in this really strange way, and then you turn it off. And that strange way is a singular arc. So we'll talk about singular arcs in a couple weeks, because it's a really interesting thing, and they're very, very difficult to deal with. But you need to at least see what goes on with singular arc problems. So we're done with the minimum time double integrator. What I would really encourage you to do is is like Kirk's book has a pretty good explanation of this minimum time double integrator. The best book I know of to describe this problem is the following book, and it's a really, really good book, and you can get it from Dover. It's Athens and Falb, and the book is actually called Optimal Control, and it's it was originally published by McGraw-Hill in 1966, and now it's published by Dover because they did a reprint of it. It costs like $15 or something like that, but it has a great analysis of this double integrator minimum time plan. And most of the notation and stuff that I've gathered here was taken from Athens and Falb because they just had a nice way of sort of distilling it down into something that was manageable. So I highly recommend you look at that. So that's our extra lecture for this week. So we're back on track. Okay.